Hello and welcome to another video on physiology. In this video, I would like to explain some of the basic terms and concepts that we use in almost every video and that are essential for you to understand. However, there may be things that you already know, so feel free to just skip these and concentrate on what's new. The first concept I'd like to explain is the membrane potential and its changes, because as you know, I use the words membrane potential at least once in every video. To understand it, let's imagine a cell which is separated from the extracellular environment by a membrane. Just to remind you, extracellular means outside the cell, intracellular means inside the cell. What's very important is that the composition of extracellular and intracellular fluid is very different. In the extracellular compartment, there's a lot of chloride anions and calcium and sodium cations. On the contrary, inside the cell, there's a lot of potassium cations and negatively charged proteins and amino acids. Now, to explain this better, let's take a closer look at only one anion, potassium. As we said, there's a high concentration of potassium inside the cell and low concentration outside the cell. And this creates a concentration gradient, where potassium inside the cell diffuses through the membrane so that there's the same concentration of potassium inside and outside. As potassium diffuses, it's leaving behind the negatively charged anions, like proteins, that are just too big to pass through the membrane, and as they are negatively charged, the inside of the cell becomes more and more negatively charged. What happens is that the negative charge inside the cell starts to attract the positively charged potassium that diffused through the membrane back inside, and another gradient, which is called the electric gradient, is established. Now, when the potassium moving out of the cell equals the potassium moving inside the cell, we talk about the equilibrium potential. The value of the potential can be calculated using the Nernst equation, which works with the different concentrations of an ion inside and outside the cell. We'll definitely cover the equation in a future video. Now I'll only tell you the values. The equilibrium potential for potassium is approximately minus 90 mV, for chloride minus 80 mV, for sodium 65 mV, and for calcium 120 mV. Now, when we get all these numbers, we use another equation called Goldman equation. Again, there will be a video covering it. For now, let's just say that the equation considers how much each ion moves through the membrane. This equation gives us the resting membrane potential, which, in this case, is around minus 80 mV. It's quite close to the equilibrium potential of potassium. And that's because potassium is the ion that travels the most. Okay, so to summarize, resting membrane potential is just the summation of the equilibrium potentials of every ion. That's it. The thing is that the membrane potential can change during, for example, an action potential, when different ions enter the cell. When we want to describe how the membrane potential changes, we usually use three terms: hyperpolarization, depolarization, and repolarization. To explain them, let's graph the membrane potential over time and look at how it changes. Imagine that our cell has a negative membrane potential of, let's say, minus 50 mV. Now let's say that some negatively charged ions, for example chloride anions, enter the cell and the membrane potential becomes even more negative. This is called hyperpolarization. If it's the other way around, and the membrane potential becomes more positive, because there's, for example, sodium cations entering, then it's called depolarization. And finally, repolarization is when the membrane potential becomes negative again after a depolarization. And then again, hypothetically, if the membrane potential became more positive, that would be depolarization again, right? This can be confusing, but trust me that by the end of the year, when you've used these three terms hundreds of times, it won't cause you any trouble. Okay? Great. So another important term in physiology is the threshold potential, or just threshold. Simply said, threshold potential is the membrane potential that the cell needs to reach to elicit an action potential. Let's look at an example. Again, let's graph the membrane potential over time, and this time, let's look at a cell of the cardiac conduction system. Now, these cells are very important because they generate and conduct electrical impulses that force the heart to contract. If you'd like to know how exactly they work, there's a whole video on them, but now we'll only concentrate on the threshold potential. So at the beginning, our cell has the membrane potential of around minus 70 millivolts. Now, as we said, in order to elicit an action potential and generate an impulse, it needs to reach threshold. So sodium cations enter the cell and the membrane potential becomes more positive. And at around minus 50 millivolts, the membrane potential is positive enough to elicit an action potential. So these minus 50 millivolts are considered the threshold potential. If we had stopped at, let's say, minus 40 millivolts, the threshold potential wouldn't have been reached and nothing would have happened. Good. So I hope everything's clear so far, so that we can move to the last part, ion channels. Ion channels are passages for ions, simply said, so that they can either enter or leave the cell. Technically speaking, ion channels are proteins, so-called integral proteins. Integral proteins are proteins that penetrate all the way through the cell membrane. This is important, right? Because we need the ion to travel through the whole membrane, not just a part of it. The second type of proteins, just for revision, are called peripheral proteins, and these do not penetrate all the way through the membrane. So these integral proteins, these ion channels, are very special in that they allow only certain ions to pass. So for example, only sodium, but not, let's say, potassium. This is called selectivity. Some of them also have gates, which open and close so that they can control the movement of ions. Now, there are two special groups of ion channels: voltage-gated and ligand-gated channels. Voltage-gated channels are controlled by the changes in the membrane potential. So they can, for example, open when the membrane potential becomes more positive, when it depolarizes. Ligand-gated channels, on the other hand, are controlled by different substances, such as hormones or neurotransmitters, that bind to the channel. Generally speaking, a ligand is a substance that binds to another, in this case to the channel, and that's why these channels are called ligand-gated. Finally, let's discuss two very often used terms in physiology: permeability and conductance. Permeability expresses how easily a substance passes through the cell membrane. So for example, if a membrane is highly permeable to a certain ion, the ion passes through the membrane very easily. And conductance is just the permeability of a channel. So it expresses how easily an ion passes through that channel, okay? So this is it for today. I hope you found this video helpful and that you reviewed some of the terms that we use in physiology all the time. For more videos on physiology or medicine in general, please subscribe. Thank you for watching, and until next time, don't forget that medicine can be easy.